Hey everyone, welcome to Control System Lectures. In this lecture, we will see some questions related to the stability of nonlinear systems and how to solve them. The theory required for solving the questions are already discussed in previous videos, and I have given the links to those lectures in the descriptions. So, if you need them, please go through them first. Let's start our lecture now. First question is, examine the stability of given system with respect to origin as an equilibrium point by Krasovskii's theorem. And the system is x1 dot equal to minus 3 x1 plus x2 and x2 dot equal to x1 minus x2 minus x2 cube. Okay, so as discussed in lecture number 19 about Krasovskii's theorem, first we need to obtain the Jacobian matrix for the system. For that, let f1 of x be minus 3x1 plus x2 and f2 of x be x1 minus x2 minus x2 cube. From this we can write dou f1 by dou x1 equal to minus 3, dou f1 by dou x2 equal to 1, dou f2 by dou x1 equal to 1 and dou f2 by dou x2 equal to minus 1 minus 3x2 square. Therefore, the Jacobian matrix for the system is equal to f of x equal to minus 3, 1, 1 and minus 1 minus 3x2 square. Let us now define the matrix f cap x equal to f star x plus f of x, where f star x is the conjugate transpose of f of x. That is, f star x is the conjugate transpose of f of x. Therefore, f star x equal to minus 3, 1, 1, minus 1, minus 3 x2 square. Now we need to calculate f cap x, and f cap x equal to f star x, which is minus 3, 1, 1, minus 1 minus 3 x2 square plus f of x, and f of x is minus 3, 1, 1, minus 1 minus 3 x2 square. Therefore, minus 3, 1, 1, minus 1 minus 3 x2 square, and this on summation gives us minus 6, 2, 2, minus 2 minus 6 x2 square. Therefore, f cap x equal to minus of 6 minus 2 minus 2, 2 plus 6 x2 square. If we write this matrix as A, we can write this equation as minus A. Therefore, checking the principal determinants of matrix A, determinant of 6 is equal to 6, which is positive, and determinant of 6 minus 2 minus 2, 2 plus 6 x2 square is equal to 12 plus 36 x2 square minus 4, which is equal to 36 x2 square plus 8, and this is always positive. So we can see that matrix A is positive definite, and as a result, negative of matrix A, that is f cap x, is negative definite, and as f cap x is negative definite, the equilibrium state at origin is asymptotically stable. Asymptotically stable. Okay, now going to the second question. A scalar function is defined as ax1 square plus 2x1 x3 plus ax2 square plus 4x2 x3 plus ax3 square. Determine the condition for positive definiteness of the function. Okay, so the theory related to this question was already discussed in lecture number 17, and the link to that video is given in the description. So if you feel like, please check out that first. Here the function is given as v of x equal to ax1 square plus 2x1 x3 plus ax2 square plus 4x2 x3 plus x3 square. Also you can notice that this is a quadratic function of the form v of x equal to sigma I equal to 1 to n sigma j equal to 1 to n kij into xi xj, where kij's are real constants. So what we have to do now is write the function v of x in the form x transpose into q into x, where q should be positive definite for v of x to be positive definite. That is, if q is positive definite, then v of x will be positive definite. So our aim is to make q positive definite. Alright, so comparing these two equations, we will get the relation qij equal to kij when I equal to j and qij is equal to half times kij plus kji equal to qji when I not equal to j. Also here we have x1, x2 and x3 present in the function. Therefore, q is a 3 by 3 matrix. Let us now find the elements of the matrix Q. We have Q11 equal to K11, that is the coefficient of the term x1 into x1, that is x1 square, and you can see that the coefficient is a. Therefore, we have Q and Q11 is a. Similarly, we will see for Q12, which is half times K12 plus K21, which is equal to Q21. But you can see that there is no term like x1 x2 or x2 x1 in this function. Therefore, the coefficients K12 is equal to 0 and K21 is equal to 0. Therefore, we have Q21 equal to 0 and Q12 equal to 0. Therefore, this is 0 and this is 0. Similarly, if we check for all the elements of the matrix Q comes out as A01, 0, A2, 1, 2 and A. Therefore, we can write V of x as x1, x2, x3 into Q, which is A01, 0, A2, 1, 2, A into x1, x2, x3. Let us now make the matrix Q positive definite so that V of x is positive definite. For this, all the principal determinants of matrix Q should be positive. That is, determinant of A should be positive, determinant of A 0, 0, A should be positive, and determinant of A 0, 1, 0, A 2, 1, 2, A should be positive. That is, A should be positive, A square should be positive, and A into A square minus 5 should be positive. And all these conditions are true if A greater than root 5. Therefore, V of x is positive definite when A is greater than root 5. Okay, that brings us to the end of our lecture, and in the next video we will come with more solved examples. Thanks for watching and have a nice day.